Mexican World Cup
Hi,
stuff.
hello, good morning. How are you? Full house, right?
Hey!
Well, we are really excited to see all of you here today. On behalf of the Merida English Library, I welcome you, and we are really happy to have this talk with Kelly Beatty about the James Webb Telescope, in order also to share some insights about the upcoming solar eclipse that is going to happen this Saturday, if the weather allows it. So please send good vibrations in order to have a clear sky on Saturday, because this eclipse will be something unique to appreciate here in the Yucatan Peninsula. So let me introduce you to Kelly. Kelly Beatty has a degree in geology from the California Institute of Technology and a master's in scientific journalism from Boston University. From 1974 to 2018, he was a full-time contributor to Sky and Telescope magazine, but remains actively involved in many Sky and Telescope articles, tours, and other projects. Kelly has been honored twice by the Division of Planetary Sciences of the American Astronomical Society. He also received the prestigious Astronomical League Award in 2006 for his contributions to science of astronomy, and the American Geophysical Union's Prize for Sustained Achievement in Science Journalism. He is my role model. Kelly enjoys speaking to audiences of all ages and interest levels about his passion for astronomy. We are really happy to have him here. And he observes when he can through one of his 8 telescopes, and he is active in fight against light pollution. So we are really happy. I forget to mention who I am, because I am a stranger from Merida English Library. I am Daniela Tarcuni. I am the head of science outreach in the School for Higher Studies from UNAM. We have a school that opened in 2018 here in Merida to have higher studies in many fields of knowledge. And I represent the local committee of eclipses that we are going to see. We will have this annular solar eclipse this Saturday, and 6 months from here, in April 8th, we will see partially and total solar eclipse. So we are preparing many venues and many activities for all of you to enjoy this eclipse. Here is also with us Trisha Olivares, which is from the U.S. Consulate. And we are doing many activities here in Yucatan prior to the eclipse. So tomorrow we will have some other conferences and many activities on Saturday. And U.S. Consulate has been a partner with us in this local committee. So I hope that you enjoy very much this talk about the James Webb Telescope. And I don't have this microphone here, and I pass it to Kelly.
Thank you very much for being here today. It's amazing that you all have an interest. Now, I'm not going to be talking about the eclipse at all, but you're probably wondering what I'm doing here. And I am here with a group of about 25 people who have come to see the eclipse. They're actually arriving in Merida right about now. And I will join them after the end of this talk, and then we're moving on to Campeche. And we are bringing clear skies with us for all of them. Annular solar eclipses are very exciting. I have seen 7 before now. I have seen 15 total solar eclipses. I've been at this a long time, so they're all different. It's exciting every time. So this is my group. We were to Chichen Itza, as you can obviously see, and we're all looking forward to our time here. I have to tell you that I have been wanting to come to the Yucatan for about 30 years. And the reason is, when the Chicxulub crater was discovered, I was at the meeting the scientific meeting where that was announced. And I was a reporter for my magazine, Sky and Telescope, and I was one of the very first people to report about the discovery of the crater. And as you know, the crater doesn't really have an expression on the surface except for the cenotes, right? So yesterday, I fulfilled a lifetime dream. I got to swim in a cenote. Okay, so today we're going to talk about the most amazing telescope that has ever been put into outer space, the James Webb Space Telescope. You can see what we're going to cover here. I apologize for those of you for whom English is not your first language. Just think of it as a way to practice. I want to talk just a little bit about the Hubble Space Telescope. And it's hard to believe, but the Hubble Space Telescope has been in space for more than a third of a century. It was launched in 1980, and it still is functioning. The Hubble telescope was designed to look at the universe in visible light, what we see with our eyes, with a little bit in the ultraviolet and a little bit in the infrared. But it is primarily for looking at the universe as we see it. It was named for one of the most famous astronomers ever, Sir Edwin Hubble, who, among other things, confirmed that the universe is expanding. Now, what does that mean, that the universe is expanding? You know, if I set off a firecracker or something like that, you know, and it goes kapow, if there wasn't any gravity, all the pieces would come back after a while. Right? They would return to the center of gravity. That's not what is happening with our universe. It's actually expanding faster and faster over time. And so he confirmed that with his observations. Now, this is what an expanding universe looks like. Looks familiar, right? Do you know how hard it was to find a YouTube video of raisin bread expanding? So imagine the loaf of bread is our universe. And this little raisin right here is the Milky Way galaxy, our home galaxy. As the loaf of bread expands very slowly, right, I am moving away from every other raisin in that loaf. Now the ones that are close to me, I'm only moving away slowly. But you can imagine that the ones on the other side were moving apart faster. That, ladies and gentlemen, is the expanding universe. Okay, so the Hubble Space Telescope, among other things, was to confirm that. And it had a problem. When it was launched, some of you who are old enough remember that the Hubble telescope was launched with a flawed mirror. It was made very perfectly, but incorrectly. And so what happened was, when it got into space, this should be a sharp point of light. And this is the kind of image that the telescope was delivering. It's like me when I take my glasses off. Everything's a little bit fuzzy. And so what happened was that NASA was very embarrassed by this. It was a very expensive telescope. Let that sink in. And so we fixed it by actually launching a repair mission, because the Hubble telescope was in an orbit fairly close to the Earth. We could reach it with the space shuttle, and the next crew of astronauts to go up basically gave it some eyeglasses to correct that, and you can see the difference before and after. So this was a great triumph. And in fact, the Hubble telescope went on to be just an amazing instrument for astronomy in general. In all, we went to the Hubble telescope 5 different times to repair it or replace things. The last time was in 2009. So it has been on its own for 14 years, and it's still working. And so we're so thrilled that it is still doing that. These are some of the great discoveries that the Hubble telescope made, and I've highlighted in yellow some of the things that were most important, just to show you that this was a very productive telescope. Now, I mentioned that it only really looked in visible light. We want to see the universe in different ways. Astronomers are greedy. They want to look everywhere they can. And so, for example, this is the spectrum of visible light, what we get from the sun. When you break it down, it gives us all these colors of the rainbow. But there is still radiation down here past violet. We call it ultraviolet. It's how we get a sunburn. Up on the top, past red is infrared. It's what's making us so uncomfortable today. The heat, the radiation. And so this is the entire what we call the electromagnetic spectrum, which visible light is just a small slice. Radiation, light energy, if you want to think of it that way, can be at any of these wavelengths. Even like your microwave is part of the electromagnetic spectrum. And so there's the I can use this. There's the Hubble telescope there at the visible light. The Webb telescope is designed to look only in this infrared band. It does not look the same places that the Hubble telescope did. It is also not the first time we have sent a spacecraft like this to study infrared. There have been others. There have been others by NASA. There have been others by other European Space Agency. But the Webb telescope is by far the most capable, the biggest, and will be the most productive. Now, why should we want to look at the universe through infrared eyes? Basically measuring the heat that is coming to us from distant objects. Here's an example. If I took a picture here in visible light, one of these animals is warm-blooded and the other one is cold-blooded. You can probably guess, but with infrared radiation we don't have to guess, because we can see the heat coming off of the meerkat, and the crocodile is the same temperature whatever water it is in. So this is an example of how infrared is a very powerful way to probe the universe. And so one of the things we want to do is imagine that you are out in space and you pass through a dust cloud, which there are many in space, a big cloud of gas and dust. How would you know? Because it's dark, it's cold, it gives off no light of its own. The only way that we could tell that the cloud is there is to look in the infrared to measure just a little bit of warmth that is coming from that cloud. And so we can capture these faint glows of dust, and dust is very common in outer space, very common. Our solar system came together from a giant cloud of gas and dust that collapsed 4.5 billion years ago. That's even older than I am. So, it was a long, very long time ago. This is a very special kind of object. This is called the Eagle Nebula. It's a very common object that amateur astronomers like to look at with their telescopes. And in the center, that little dark patch was made very famous by the Hubble Space Telescope. You might have seen this before. These are what are called the pillars of creation. And they are creation in a very real sense. Some people say it's like the hand of God, okay? But up at the tip, in these little fingers, stars are being born right now, coming together from the gas and dust. Just like in your house, you probably have lampshades on some of the lamps in your living room, and at night, you don't know that the lampshade is there until you turn on the light. And so in the same way, we can't see these dust clouds, but because there are stars, new stars that are just giving off their first light, inside the cloud we can see them. This is what it looks like in visible light. Here, this is the power of infrared, because we can actually look through the dust to see what is inside. So this is just one example. So these are some kinds of things that can be studied. All different kinds of objects in the universe are warmed, and so we hope to study them all. And especially, we can use infrared light to show us parts of the universe that we have never been able to see before because they are so far away. Now, I know you may not have ever thought of it this way, but in space, distance is a time machine. The sunlight that is striking those of us when we walk outside left the sun about 8.5 minutes ago, traveling at the speed of light that has reached the planet Earth. The nearest stars are about 4 light years away. That means they have traveled, the light from those stars has traveled 24 trillion miles, about 40 trillion kilometers, to reach us, and it's taken 4 years to do that. So the light from nearby stars that we see left those stars maybe 5 years or 50 years or 500 years ago, and the farther out we look into space, the farther back in time you're seeing. You're seeing that light as it left those objects, however long ago they are. There's a problem, however, because the farther away, remember the raisin bread? The farther away we look, the faster that object is moving away from us. And as it moves away from us, something happens to the light. It gets stretched out. You're probably familiar with this. Think of a car horn. If the car is standing still and you honk the horn is always giving the same sound. But if that horn is on a crazy taxi coming at you down the street, something interesting happens. As it's coming toward you, the pitch of the taxi horn is higher, and after it goes by, it's lower, just like this. That's a phenomenon called the Doppler effect, and the same thing happens with light. So because the universe is expanding and expanding faster, accelerating faster, out on the edges of the universe, what started out as visible light, by the time it reaches us, is not visible light anymore. It's been stretched to the infrared. So if we want to see the most distant objects, the most distant stars and galaxies, we need to look in the infrared or they will be invisible to us. And that's what the Webb telescope is designed to do. Look at the most distant objects in the universe it can. So, why is it called the Webb Space Telescope? You know, NASA has a habit of naming its big observatories after people who have been famous astronomers in the past, like Edwin Hubble, like Suryakanth Chandrasekhar, Lyman Spitzer. These were all famous astronomers. So, who was James Webb? Well, he was not a scientist. He was not an astronomer. He was a career diplomat for the United States, and in his later years, he became the director, the administrator of NASA during a very critical period when NASA was building the Apollo spacecraft that would travel to the moon and back. And he was also a big proponent of space science. NASA was not initially in the science business. And you know, now we kind of think of NASA as like doing only science and launching occasional astronauts. But it's a very major scientific organization, and James Webb was one of the people responsible for that. So the telescope is named after him. It's taken a long time to get this telescope into space. It was originally conceived almost 30 years ago as an enormous infrared telescope in deep space. The telescope would be up here, and then this would be a big sunshade that protected from the light from the sun, because that would sort of swamp the detectors and you wouldn't be able to see warm objects anymore. But it had a very tortured history of this project. In 2005, it was completely redesigned into the design pretty much that we ended up with. And instead of being launched, as early as 2013, the problems continued. And so, in the end, we got the telescope we wanted. On the right are the mirrors of the Webb Space Telescope. It's not just one mirror, but it's 18 different mirrors, each in the shape of a hexagon, pieced together like a giant honeycomb. Each of those mirrors is about 4.5 feet across, 1.5 meters more or less, and you can see how much bigger it is than the Hubble Space Telescope mirror. With that extra diameter comes the ability to see not only objects fainter, but also with more detail. I won't get into the physics, but the bigger your telescope, the finer the detail you can see, and also the fainter. So, here's another comparison with some of the other telescopes. It is a really big spacecraft. Too big to fit in the nose cone of any rocket that we have. And so, when it was finally designed and finally launched, by that point it had cost $10 billion, and it's a very expensive telescope, and this is a couple of images showing it during construction. And this is, you can see people here to compare how big it is. You can see the hexagons. The structure kind of folds up, but the mirror is still too big. So the mirror has to be able to fold up, right? A little bit like a origami style, so that it will fit in the nose cone of the rocket that went to launch. But the real key to its success is this heat shield. It's actually 5 layers of very thin material. And on the front surface, when the sun is hitting it, the temperature is quite hot, even hotter than today, for example, as much as 125 degrees Celsius. But on the back side, after all of that light has been reflected away by the different layers, it's very close to absolute zero, which is what you want for a sensitive instrument like this. It's a very multinational project. I confess I'm very sorry there's no contribution from Mexico itself. But many scientists here in this country will be allowed to participate in the analysis of the results. but in terms of cooperation in building the telescope, there's something I'm getting looked at here. We'll skip that. This is what it looks like in outer space. The mirror is here, and there's a second mirror right there. So all of the light strikes from an object, strikes this, gets funneled like a magnifying glass to this point, and then all the instruments are back here, and then this is the sun shield down here on the bottom. Now, I won't get into the technical details, but there's 4 instruments, and they all study the infrared. Some of them are there just to take pictures at different wavelengths of infrared light, and some of them are what we call spectrographs. If you imagine the colors of a rainbow, right, then some of them are studying the individual wavelengths, the blues, the yellows, the reds, for hints about what the composition is. Those 4 instruments don't point in the same direction. They're all pointing at slightly different places in space. And this is what I'm talking about. The sun, when you see a rainbow from the sun, it's a continuous spectrum. But you see the colors blend very smoothly from one to the other, at least at low resolution. But what the Webb telescope is doing is looking at specific lines. You probably never realized this, but a fluorescent light bulb, which most of us have in our homes, including those little squiggly ones, the compact fluorescent, don't give off white light. They don't. They give off a very few wavelengths of red light, blue light, and green light only, the peaks in this graph. And when your eye sees them, it combines all of those inputs and says, oh, I'm looking at white light. But you're not really looking at white light. And that's why fluorescent bulbs are so efficient, because they don't have to create a continuous spectrum. They only create certain lines. So I know that sounds complicated, so I'm going to give you a little demonstration with a balloon. Imagine this is an atom. All right? This is an atom in its rest state. Atoms contain small particles, protons, electrons especially. And when an atom is at rest, it's okay, that's fine. When an atom is at rest, it just sits there. Most of the atoms and molecules in our atmosphere are all at rest. Sometimes a pulse of light at a particular wavelength comes along and it excites that atom. Now that's one breath worth of excitement for that atom. Okay, and you can imagine that now it's under a little bit of stress. If I were a more energetic photon, it would excite the atom even more. So how does this atom get rid of its light, get rid of this excess energy? Now it's back at rest. It gave off the energy that it absorbed, and we see that as very specific wavelengths of light. And so consequently, when we look out into space and look at different objects, we see, now I'm going to skip it. This has got a British accent. No one would understand it. When we look out at space, we can see different elements and know that they are there simply by the light that they are giving off at specific wavelengths or the light that they are absorbing at specific wavelengths. And so this is what those spectrographs aboard the Webb telescope are going to do. Let's skip that. And so we can use these spectra, not pictures, but actually we're dissecting the light into different wavelengths to tell us a lot about the atmospheres of planets or the velocity of gas or even the temperature of stars. Now I can go back to this. Stars have different temperatures. Many of you have cooked on a gas stove or a gas barbecue grill, and the color of that flame is blue. And a candle has a flame that is, if you've got a blue candle, I would like to see it, yellow, right? And the thing is, we grow accustomed to the notion that red is hot and blue is cold, but with light, it's just the opposite. That gas flame is much, much hotter than a candle flame. And the same is true with stars. So this is a plot that shows the peak emission, how much energy is being emitted at different wavelengths of light depending on the temperature of the star. There are blue stars that are much hotter than the sun that look blue. There are yellow stars, this is like our sun. There are red stars that are much redder than our sun because they are cooler than our sun. So in this case, red means cool objects and blue means hot objects. We can use the Webb telescope to tell all of these things. So here are some of the things that we're going to study, and I'm going to try to get to some of the objects that we have first. I would like to share with you how the Webb telescope got launched. It was launched not from NASA, not by NASA, not from a NASA rocket, not even in the United States. It was launched in French Guiana at the launch site of the European Space Agency, because the Europeans, with this rocket called the Ariane 5, had the only reliable rocket powerful enough to launch the Webb telescope into orbit. Not even NASA had a powerful rocket. So this is the launch, a replay.
T-minus 30 seconds to count. Standing by for terminal count.
I'm sorry that the sound isn't louder. But the countdown's going to be in French.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
Everybody have a good start. And look at
And away it goes. Very successful launch. We can watch the spacecraft heading out into space. Unlike the Hubble Space Telescope, the Webb telescope is put very, very far away from the Earth, because the heat from the Earth would mess up all of its delicate observations. So we want to get as far from any source of heat as possible. And so we parked it at a place called the Lagrange point, which is 1 million miles, 1.5 million kilometers away from the Earth. Wow. And it will stay there forever. We can't recover it. We can't repair it. It's just going to be there indefinitely. And these points are kind of a gravitational watering hole, if you will, where the balance between the Earth's gravity and the Sun's gravity allows them to stay in that location without having to fire any rockets occasionally. So that's where it's going to be. And of course, it was all folded up inside the rocket. So between here and there, it had to unfold, and this is that story. Well, that was very nice. Now comes the hard part. This is the part of the lecture that's going to make your head hurt.
Yes.
We're going to try, one of the main goals of the Webb telescope is to try to look so far into the distant edges of our galaxy that we're looking close to the beginning of our universe, which was 13.8 billion years ago. For context, our solar system is 4.5 billion years old, roughly 1/3 of that age. And so, in order to see that, it turns out that this Big Bang that happened to create our universe was a super hot event. It was so hot that there was nothing comparable to the atoms and molecules that we have today. Everything was a soup of subatomic particles, protons and electrons. And because of that, light, even though it was very, very hot, light could not escape, because every time a little bit of light got emitted by one of those particles, it would get absorbed very quickly. So the universe, in its earliest stage, was very hot and very dark. And it wasn't until things started to cool down and atoms formed, in this case I'm showing hydrogen atoms, that the light was actually able to escape, and suddenly the universe lit up. And that point happened 380,000 years after the Big Bang. We know that from the computations. And at that point we saw that, if we were around at that time, we would have seen this very, very hot fireball, still thousands of degrees. Over time, as the universe has expanded, the light from that event has gotten stretched and stretched and stretched to ever longer wavelengths, so that now, So that now, if we look out into space, we see this dull glow at radio wavelengths. It's called the cosmic microwave background. You can think of this as the echo of the Big Bang. And you need to see this with the radio telescope. 2 American scientists won a Nobel Prize for detecting this radiation for the first time. And if you look closely, you can see that it's not all smooth. It's not all the same temperature. The little blues and reds are showing us changes from one spot to another of just a millionth of a degree. But that was enough to give our early universe places to create concentrations of matter, concentrations of gas and dust. So our goal, we can't see back to the Big Bang. We can only see to this point 380,000 years after its beginning. Hubble tried. It looked back to within about 1 billion years of the beginning of the universe. And then it tried. So we're looking for the evidence for the first stars and the first galaxies up here. We have to look very far back in time. Hubble tried again late in its career and got even farther, but not quite back far enough to where we could see those very first galaxies. This is, I think, I'm actually going to skip that in the interest of time. So when Hubble looked back, made this very, very long exposure, taking over 400 orbits, weeks and weeks and weeks, it revealed this image that you see here. This is called the Hubble Deep Field, the Ultra Deep Field. Everything you see, with the exception of this object here with the spikes on it, I don't see any others, everything you see in this image is a galaxy. Not a star, it's a galaxy. There are so many galaxies here, and the redder they are, you should know this by now, the farther away they are because they're moving away from us faster and faster. And so their light has begun to shift to the infrared. So this is the kind of thing that Webb telescope was designed for. What Hubble saw was that, now, or relatively soon to now, galaxies have a very mature kind of shape. They're beautiful spirals, or they have a very defined shapes. But as Hubble looked back farther and farther, closer, this is 1.1 billion years, 1.8 billion years after the Big Bang, you can see that the galaxies, well, maybe you can see, were really kind of just, dust balls. There wasn't really a lot of shape to them. And so astronomers thought that this was their model prior to Webb. They thought that the very earliest galaxies were just kind of immature, undeveloped blobs of stars without a lot of form and also without a lot of mass. Well, Hubble couldn't do this as well as Webb is. It's exploiting something called a gravitational lens. If you imagine here, there are many places in the universe where galaxies clump together to form big sort of beehives of galaxies, and they have a lot of mass associated with them. Now, Albert Einstein was the first to realize that mass can bend light. Mass can bend light. And so when we have an even more distant galaxy or something that's much farther away, as that light comes by this cluster, the cluster acts like a magnifying glass, sort of a lens to take that light and concentrate it so that here on Earth, we can actually see this galaxy that we otherwise wouldn't have been able to do. So here's a great example of that. This is a Webb telescope image, one of the first that was returned. And this is a star. Pretty much everything else here is a galaxy. The whitish ones are relatively close by. The orangish ones are very distant. And the ones that have this kind of arc to them are galaxies at the extreme distances that have been magnified into view by this gravitational lensing effect. And so they don't look very pretty, but we can definitely study them and we can learn what these galaxies are like. And this is to show you two different images at different wavelengths of that same image. This is at something pretty comparable to human vision, but just a little bit in the infrared. This is deep in the infrared, and I won't try to explain the differences. But what we see now, we can now see back much farther than Hubble was able to do. And we were able to see that some of these galaxies, right, the Z number is an astronomer's measure of how far away they are, how fast they are receding from us. And what we have found, to our shock, not my shock, but their shock, is that those early galaxies are not just amorphous blobs. They're actually very well developed. You can see some blow-ups here. Oops, let me go back here. You can see, these have definite shapes. There's little spirals and stuff. Here's a better example. These are galaxies that are 11 billion years old, and yet they have a lot of form and function. And there are a lot of them, and they're bigger than anyone expected. So all those astronomers have gone back to the drawing board to try to explain what the Webb telescope has already taught them about the universe that was different than what they believed at the beginning. Some of those galaxies, early ones, also have a lot of dust in them. This is a little bit subtle, but in the very early universe, there were really only 2 or 3 elements. There was hydrogen, there was helium, and a little bit of lithium and beryllium. Nothing else. There was no iron, there was no oxygen, none of those things. And so what they're finding is some of these early galaxies have dust, which means carbon and other things that shouldn't have been there this early in the development of the universe. And so that is an amazing result. And we've now seen this one star otherwise this is a gravitational lens chunk of this image here. This is actually a solitary star that seems to have formed only 900 million years after the Big Bang. Only 900 million years. Seems like yesterday, right? Okay, so that's the key findings that have come from the Webb telescope regarding the distant universe. I'm going to show you some things that are a little bit closer in, that have a little more relevancy to us. This is the Large Magellanic Cloud. It's kind of like a satellite galaxy to our own Milky Way, a groupie, if you will, that you can see from the southern hemisphere, and I'm pretty sure you can see from here. Your latitude is 21, I think, here. And so this is about 163,000 light years away from the Milky Way. It's on the outskirts. It's following the Milky Way around. There is a nebula called the Tarantula Nebula. We're going to zoom in on that. And this is what an image of the Tarantula net looks like to a telescope from here on the Earth. Now we're going to zoom in a little bit farther, and this is what it looks like to the Webb Space Telescope. I call your attention to this. This is essentially a brand new star, a newborn star. Imagine when you were born, if you were so bright that it blew your parents out of the house. Wouldn't that be something? This is what's happening here. This star, when it's young, it puts out a prodigious amount of very high energy radiation, and it creates a hole in the cloud from which it was formed. So you can see it's kind of blown a hole open here in this nebula. And this is again 2 different wavelengths showing you. With these longer wavelengths, we can see details in the gas cloud that we can't, but you can definitely see the star. And this is, I showed you this because I want to just give you a taste of the power of this telescope. You remember back to the spectrum, the balloon, right? We can look at the light coming from those dust clouds, and we can tell how much hydrogen there is, how much dust there is, how much other, just from analyzing the light. Right? We don't need to go there and run a chemistry experiment. A little bit closer in, this is now 9,000 light years away. This is the most beautiful nebula in the southern hemisphere. You can see this from here, not at this time of the year, but around the winter, February, March. It's down. Many of you, I'm sure, have seen the Southern Cross. Take a right turn at the Southern Cross, and the Brennan Nebula is there. And it is a massive factory forming stars right now. And the biggest star in sight is 80 times the mass of our sun. It's an enormous superstar, and it's very unstable. Any day now, it could go supernova. But because it's 9,000 light years away, we wouldn't get the message until 11,000 AD, if it happened today. Or maybe it's already gone supernova and it just hasn't gotten there. We just don't know. But let's zoom in, and in a similar way, right? You see these spikes? These are what are called diffraction spikes. It's an artifact of the imaging system. There's a big spike right here, and up here on the ceiling is a star that has blown open one of these holes again in the gas and dust. They're just beautiful. I don't need to try to explain what the science is that's going on. They're just beautiful to look at. And that's my mantra, by the way. Astronomy doesn't have to be hard. It can just be beautiful. And that's what we're looking at here today. Remember the fingers of creation, Messier 16, the Eagle Nebula? All right, so this is what it looks like to Hubble here, right? And this is what it looks like to the Webb Space Telescope. A little bit more ghostly, I think. And we're now seeing into those dust clouds and understanding where the stars are forming. For example, look right here. You wouldn't know it looking at this, but here's 4 stars in a cluster that have formed, hidden from view by this dust, but it's easy pickings for the Webb Space Telescope. Same thing is happening here. This is what's called a ring nebula, a planetary nebula. This is the fate of our sun. Our sun will never become a supernova. But, like humans, in their old age, it'll get bloated and cranky. And at some point, it's going to have just a sneezing fit and lose its outer layers. Maybe too much information for you, but imagine you sneeze so hard that all your skin flies off. That's what will happen to our sun near the end of its life. And what will be left behind is a fraction of what was formerly the sun. This is a previous image from the Hubble Space Telescope. With the infrared eyes of the Webb telescope, we see that there's actually 2 stars there, not just one. All right, so I think most of us have seen the beautiful constellation of Orion, which will be rising in the evening pretty soon now and be dominant all winter long, all December through, say, March. You might have seen the beautiful Orion Nebula, which is right here, one of the most beautiful objects in the nighttime sky in the northern hemisphere. What you might not realize is that when we look at Orion in the infrared, it is chock full of these dust and gas clouds. And in fact, the Orion Nebula itself right here is a cauldron where thousands of stars are forming right now. It has been studied with Hubble, with many telescopes over the years, to try to pierce the cloudy veil, the fog in front of us, so that we can get at the stars. With Webb telescope, this is very, very easy, and this is a result from just the last 2 weeks. Right? I wanted you to have something fresh to remember me by. It turns out that in the middle here, there are 4 stars which are called the trapezium. These are 4 very young stars. Those 4 stars are responsible for lighting up the whole nebula like that lampshade. And when we look at them very closely, we see lots of young stars being formed, but astronomers have just discovered that there are pairs of objects that have no star. They're much more massive than Jupiter, maybe 10 to 20 times the mass of Jupiter. They're not stars, they're just super humongous planets, or here they call them Jupiter mass binary objects, or jumbos. Scientists have a knack for this kind of stuff. And you can see maybe here that there are 2 here and 2 here. So the first thing that's interesting is that they're on their own. They're rogue planets. They're not in the solar system. They're not attached to a star. And we know of some rogue planets. We've never seen 2 of them before, side by side, and there are all kinds of them in the Orion Nebula. Again, they have no explanation for why these should exist. They have gone back to the drawing board. This is exactly how science works. Somebody makes a hypothesis, somebody else goes out and makes observations that either prove or disproves that hypothesis, and oh, by the way, what do you want to do about these, theorists? And the theorists say, Jesus, we don't know. And so they're going to try to figure this out in the weeks ahead. A little bit closer to home, this is the planet Jupiter, as seen by the Webb Space Telescope. This object right here is the Great Red Spot, which, by the way, has been shrinking over the last decade. Now it's sort of the not-so-great red spot. Jupiter is a big planet. It's 11 times the diameter of the Earth, so this is still much bigger than the Earth itself. You get a sense, maybe you can just see there's a little strip here. That's the ring of Jupiter. Who knew Jupiter has a ring? But it does, and this is one of its satellites. This is a close-up of Jupiter in the Great Red Spot, showing us details. This is now, we're measuring the heat. Jupiter is a gaseous planet. It has no solid surface. No solid surface. If you fly by in a spacecraft and dive in like you're heading into a cenote, nope, not going to happen. You just keep flying down through tens of thousands of miles of cloud until you incinerate. But, so we're measuring the heat here. I don't propose any of you do that, by the way. So we're seeing the heat coming off of Jupiter. Similarly, this is the heat coming off from Saturn. Now, unlike Jupiter, you notice Saturn's kind of invisible. We're seeing the rings of Saturn, but we're not seeing the ball of the planet itself. And this is, you're saying to yourself, Kelly, why is that? Say, Kelly, why is that? I'll get you around sooner or later. All right. So the rings of Saturn are made of water ice primarily, and they reflect. They're solid objects. They're just like if you have an ice cube or snow, it reflects all the light that's striking it. That's why it looks white. It's reflecting the whole spectrum. That's ice. So these the icy particles in the ring are reflecting sunlight, and the whether it's infrared or not, and the Webb telescope is picking it up. The planet is dark because Saturn's atmosphere has a fair amount of the molecule methane, natural gas. Right? Up where I live, where it actually gets cold sometimes, we use methane as natural gas to heat our homes in the wintertime. Methane is a very powerful absorber of infrared energy, of infrared wavelengths. And so since the Webb telescope is only looking at infrared, Saturn has absorbed all of the infrared that it receives from the sun, and it's not reflecting any of it back, which is why it looks dark. This is a cautionary tale for Earth, by the way. You, I'm sure, have heard about the role that carbon dioxide plays in global warming. The way that works is the sun beats down on the Yucatan Peninsula and heats the ground, and it does a very good job of doing that. And then the ground is hot, and so the ground gives off heat, right? Not light. Of course, it reflects the light, but it also gives up heat, especially at night, and that heat goes up in the atmosphere and tries to escape to space. Well, guess what? The carbon dioxide in our atmosphere, the water vapor in our atmosphere, blocks that heat. It absorbs it, and so the atmosphere gets warmer. Methane is the killer bee of atmospheric absorption. Methane absorbs far more readily than carbon dioxide or water does. Fortunately for us, there's very little methane in our atmosphere because the oxygen combines with the methane to make it some other organic compound that is different. However, there's a lot of methane trapped on the Earth. Way up in the polar regions are vast tracts of land that are frozen solid. The ground is frozen all the time. It never gets warm enough for that ground to thaw. In past times, that area had a lot of vegetation. So think frozen peat bog, and you get an idea of what's up there by the millions of square miles in Siberia, in northern Canada, in Alaska. If that territory were ever to melt because of global warming, because the atmosphere is warm, then all of the methane that's trapped there now would be released, and it would be game over from the standpoint of global warming. So we don't want those permafrost areas to thaw out because it would be very, very bad. All right, the last thing I want to talk about is a really interesting technique. We are very interested in the planets of other stars. Now, if I were giving this 30 years ago, I would have said, well, there are no planets around other stars that we know of. There's just the sun. But we have discovered that many, most, maybe all stars have had planets around them at one time or another. We know of more than 5,000 planets around other stars. Let me repeat that. We know of at least 5,000 planets around other stars besides our sun. We are nothing special here. Well, I think you're all special, but in a cosmological sense, our solar system is nothing special. Now, because those planets are orbiting their stars, the stars are very bright, it's hard to see the planets, to use a telescope to record them directly. But astronomers have a trick. This is just a couple of the rare cases where we blocked the light of the star in the middle and we can pick off the very few planets that are around it. But this is the exception rather than the rule. But astronomers discovered a new trick about 20 years ago. I want you to imagine that you're sitting on a porch and it's a lovely day. You're just sitting there admiring, what's going on. And it's getting to be evening. The porch light comes on and you're just looking out and you see across your lap a flicker of light, a little shadowy something. And you look up and there's this giant moth that's flown in front of your light bulb. And it's cast a momentary shadow on your lap. So you know that a moth went by because of the dip in the light that reached your lap, even if you can't see the moth. Everybody still with me? It turns out that the fraction of the light covered by that moth, it doesn't matter if that light bulb is 3 feet away or 30 feet away or 30,000 miles away. the amount of light covered by the launch as a fraction of the total light is the same. And so we can use this to see evidence that planets are crossing in front of their stars. We can't see the planet. All we see is a dip in the star's light that lasts for just a while, and then it repeats. When the planet comes around again, it repeats. And so we get a sense of how big the planets are, what the size of their orbit is, what the temperature is on those planets. And those little dips are very diagnostic. It could be a small planet around a big star, or a big planet around a small star. This technique, which is called transits, is it's revolutionizing how we search for planets around other stars. But wait, now imagine that one of these planets has an atmosphere. As it's going in front of the star's light is blocked by the planet itself, but some of the star's light is going through the atmosphere of that planet to reach us. And guess what? We can use that spectra process again to determine what the composition of the atmosphere is of a planet that we can't even see. And that's what Webb has done. This is a simulation of the kinds of molecules we can look for. Ozone, methane, water, there's other carbon dioxides down there. All of these are within, and the thing is, because these are molecules, their spectrum are in the infrared. If we went looking for this stuff with the Hubble Space Telescope, we wouldn't see it. But because of the Webb's infrared sensitivity, we can see it. And so this is a real spectrum, which is what these are called, from the Webb telescope, showing us a distant, they get these funny names. This is from the Wide Angle Search for Planets. That's what WASP stands for. And this is an actual Webb spectrum, and it's picked up the evidence for water in this distant planet that's more than 1,100 light years away from us. And this is even more recent. This was released about 2 months ago. It is an even better spectrum, and we can see methane in the atmosphere of this planet, carbon dioxide, and a hint, not a confirmation, of something called dimethyl sulfide. Why should you care about dimethyl sulfide? Because as far as we know, the only way to get dimethyl sulfide gas is from rotting biology. And so this could be a tracer, a proxy for life going on this planet. I wouldn't bet the farm on this, because it's a very tentative, you don't see much of a change in the spectrum here. It's a very tentative thing. We've been fooled before, we could be fooled again. But this is just an example of the power of what the Hubble Space Telescope has done for us. And so, ladies and gentlemen, the Hubble telescope has been taking science data for about a year. It has an expected lifetime of anywhere from 10 to 15 years. It's already blown the socks off of a lot of the theories that we thought we had about how the universe was formed, either very early or currently. It's going to be, we haven't seen yet all of the power that it's going to bring to bear to studying the planets of stars very near us, within maybe a few tens of light years. The reason that's important is the closer that planet system gets to us, the easier it is to pick off the planet separate from the star itself. And so you'll start hearing more and more about the planets that the Webb Space Telescope has started to explore, along with lots of other discoveries. So on behalf of the English Library and the U.S. Consulate here, I want to thank you for showing up today. That's it from me. Thank you very much. So I'll take some questions in a sec. Yeah, I have 5 or 10 minutes. Okay. So what we'll do is I'll get my coffee, which is the water of life here. And if you raise your hand and tell me the question, we'll repeat it. Go ahead.
Hi. My question is, when you were showing the image of the telescope unfolding, where did those images come from?
So it was an artist's animation. It's computer graphics.
Okay.
Her question was, I was showing the telescope unfolding with the beautiful walls in the background. That's just a computer animation of what is supposed to happen. Yes, sir.
I've read on the internet, so please take that with a grain of salt, but that we, with the Webb telescope, we've actually been able to see beyond the Big Bang and beyond time as we're able to conceive it. Is that actually a truth?
No, it's not. His question is, has the Webb telescope actually seen beyond the Big Bang, beyond the beginning of time even? No. And in fact, there's a raging debate right now is, what is the edge of the observable universe? Right? Have we, even if we get back to where we are, is there more universe because it's been racing away from us so fast that even though we're hoping to see the beginning, it's now past the point and going away faster all the time. That's dark energy and a talk for another day, is that the light will never have enough time to reach it, so we may never see the edge of our own universe. As far as going back to the beginning of the Big Bang, no, there's no truth to that. So I'm sorry. I would like it to be so. Yes, go ahead. Oh, I'm sorry. Go ahead. Go ahead.
Okay, I have a couple of questions. First of all, you were talking about there's a technique to see the elements in the atmosphere.
Yes.
Does this technique could lead us to find new elements in the atmosphere?
Okay.
Different.
Great question. So can we use the spectra that the Webb telescope is providing us of the atmospheres of these exoplanets to discover new elements? Well, not new in the sense that we don't know they exist, but new. For example, the dimethyl sulfide is a molecule that doesn't exist in Earth's atmosphere because it combines with the oxygen. So if we find it in an atmosphere, it would be the first time that we have seen it in an atmosphere by itself stable. Any other question?
The color of stars. You were showing us that the stars have different colors, but we know that, for example, stars, even when we say it's a yellow star, if you go to the space, it's a light. It's a white light.
Right.
Are all stars? If, for example, someone in front of a red star, you are going to see a red light or a white light?
Right. Okay. Great question. He's asking about the colors of stars and what's really the color. Like our sun, we call it a yellow star, but it doesn't look yellow. So think about a rainbow. All right. A rainbow has a range of colors, and when we combine all of those colors, we see white light. Now, it turns out that the spectrum of the sun's output has its peak, where it's putting out the most energy is in the yellow part of the spectrum. And so that's why we call it a yellow star, because that's where its peak is. Now, it is true that you can see colors in stars, and they're subtle. They're really subtle. But for example, you can go out tonight, if it's clear, the next night it's clear, way over in the west is a very bright star off the end of the handle of the Big Dipper called Arcturus. Arcturus is a red giant star. If you pay close attention, compare its light with the light of Vega, which is almost directly overhead. All right? Vega is a white hot star. It's hotter than the sun. And if you pay really close attention, you can convince yourself that Arcturus is actually redder than Vega. Or in Orion, you can convince yourself that Betelgeuse, which is up in the shoulder, which is a red supergiant, is redder than Rigel, which is down in the knee. So, our eyes are not exactly equipped well to do this, but the Webb telescope definitely is. Okay, your question, go ahead.
Yes. Why did they change the mirror to the hexagons? Is that just for design, like it's easier to unfold it?
Right. So her question is, why is the shape of the mirror, the individual mirror segments on the Webb telescope a hexagon? Well, first of all, it allows them to fit, without any wasted space. And second of all, there's a limit so remember, we're having to create 36 pieces of the mirror that will eventually have to work together as a whole. And that ultimate surface has to be really precise. So I didn't have time to describe it, but behind the mirrors are little pistons that go in and out a little bit to make sure that level is maintained. We actually do that with telescopes here on the planet Earth. Some of the biggest observatories that we have, because there's a limit to how big we can make the telescope mirrors, are actually combinations of segmented mirrors. The most famous of these is on Mauna Kea, the Keck telescopes. There are two of them, they're identical twins. They have an effective diameter of about 10 meters. That's from here to that tree back there. right? But it's made up of individual hexagonal segments, all of which they fit together very closely, so there's no wasted space, and they're all individually controlled so that they become part of this whole. And so it was that design that allowed them to find places to fold it, so that when it opened up, it would sort of snap into place and make this effectively one large mirror out of the hexagon. All right, I'm going to take one more, and then I actually have to go rejoin my group. This is anybody else? Go ahead.
Where in Campeche are you going to see the
Yes, where in Campeche am I going to see the eclipse? It's a state secret. Now we're going to be part of the party on the Malecón. We're staying at the Gamma Campeche Malecón. Our group is 25 there, and it's kind of a private spot because the hotel's not going to let other people join us. But it's going to be a party. I guarantee you, it's going to be a party. And so I hope you all get a chance to see the eclipse, right? And remember it, and then not burn out your eyeballs. Thank you again for coming today.
Here, I remember just one. We will have another talk. It's tomorrow at El Gran Museo del Mundo Maya in the North Great Museum of Mayan Work. Do you know it? Near Galerías. We will have a lecture about OSIRIS-REx mission, which is the latest mission, one of the latest mission of NASA. This lecture will be with Dr. Humberto Campins.
Oh, Humberto Campins! Tell him I said, I've known him forever.
Well, maybe you can...
I made him famous.
So all of you are invited, please. This lecture will be at 6 p.m. So maybe you can arrange your schedule and also be there with us. It will be our pleasure to see you. We will have here at the English Merida Library some activities in the eclipse, during the eclipse. And for all the people that doesn't have right now eclipse glasses, please come with me and I will gladly give you one. And thank you so much, and thank you Merida English Library for